So it's 2:02. Hi, everybody, and welcome to this first EMH webinar. My name is Edouard Clément. I'm the Executive Director. I'll be just saying a few words to start the day. I'm here today with my colleagues, Dr. Jacob Monroe from UVic. He'll be able to present some introduction materials around silver and copper models. Before we start, so just to be clear, so we're going to be recording this webinar, so you can have access to it later down the road. We'll also share with you the slides, and we'll send your way a short satisfaction survey after the webinar today. We have full house, a lot of participants, so typically you should be able to ask some Q&A in the Q&A box. And I'll try to manage questions as we are presenting the webinar. But if some of your questions are not answered during the days, feel free to reach out to us. We're going to share different ways to do that at the end of the webinar as well. So the way we're going to work, I'm just going to do a 2-minute introduction about the EMH. Then I'll let Jake present about silver and copper, and we'll try to keep at least 10 minutes for Q&A at the end of the presentation. So if I see some... I'll first start the webinar by acknowledging the financial support of NRCan. And of course, I want to thank our funding institution, Polytechnique Montréal, Institut d'Énergie Trottier, University of Victoria, and School of Public Policy at University of Calgary. These are the founding members of the EMH. And maybe one slide about the EMH. So our mission is really to provide timely evidence-based policymaking to support different stakeholders and their needs around maintaining and developing different types of models. The EMH has a role to host those open source models, and our goal is really to facilitate access to energy modeling expertise and tooling. We have 3 different areas of, I would say, expertise. We do develop and support open source tools with our partners. We have a public data repository. We are working on several visualization tools. We have an exhaustive inventory of model and expert, and we are hosting different open source models. We're going to talk about 2 of those today. This is our first pillar. Second pillar, it's about providing resources and what we like to call modeling as a service to the community. We are working on several technical documentation materials. We are building this annual survey on the state of modeling in Canada. We support different stakeholders in their needs toward finding good resources to do modeling. And we are building different sets of use case and report to support you guys on this. And finally, we have a big pillar around convening and training, where we are hosting this kind of workshop like we're doing today. Some of you are already aware of the annual forum. We're going to soon share with you the dates of the upcoming forums for this year's. We are developing different webinars with our partners as well, and we are trying to build this community of practice. So we strongly encourage you to follow us on LinkedIn and also visit our website to be sure that you don't miss any great information about what we're upcoming event and training we might be offering. So without further ado, I'll let Dr. Jacob Monroe, which is based in at UVic, but is working with us at the EMH, that will be introducing the silver and copper models for the next 40 minutes or so. So the floor is yours, Jake.
Thank you, Edouard. I really appreciate the introduction. It's nice to get things going. I think we've talked about a lot of things here since we started the EMH. And got things kicked off. You've heard a lot about the coders database. You've heard a lot about the EMH common platform that we're developing, also alluding to a lot of the visuals. Today is about 2 models in particular that are the initial models in our modeling suite. And so they're really doing a lot of the magic. And so the idea here today is to give you an idea of what those 2 models are, why you should be excited about them, and where you should locate the resources about them if you're interested in learning a little bit more. We only have like an hour today, so you're not going to learn every bit about it if you've never done production cost modeling or capacity expansion and planning modeling, but I'm hoping that we can give you a bit of impetus and motivation today. So the first thing I'm going to do is talk about the copper model, which is the Canadian Opportunities for Planning and Production of Electricity Resources. So copper is the capacity expansion and planning framework for the electric grid that we have in our arsenal. Okay, it's a multi-period and optimization-based mixed energy and linear programming model, or an MILP. It's implemented on the national system to include federal policy, but includes provincial level policies as well. We'll talk a little bit more about the resolution of copper because I think that's something that's evolving week by week here at EMH. But first, let's give a little bit of credit to the original model that I believe that copper was developed on top of, which was the CREST model, which was the Canadian Renewable Electricity Storage and Transmission model. So copper was built by extending the CREST framework. CREST was developed by Doctors Brett Dalter and Nicholas Rivers at the University of Regina and the University of Ottawa, respectively. Again, this was a capacity expansion and planning model for the electric grid in Canada. This is one of the first, at least, open source models that existed. And so I'm looking here ahead. So it optimizes the size and location of generation fleet, as well as the transmission network expansion. And we've given you here the source on the bottom there. But what I really wanted to say, this is really a point A to point B model. So you have a base year of, say, 2020, and then you have a future year of 2050. It's not evolutionary. There's no steps in between there with the CREST framework. So naturally, we had to extend that a little bit and make something that was a little bit more tuned for the Canadian system, given that there are going to be different policies that are released a long time. So it's important to see where the trajectory of that decarbonization pathway is, not just the beginning and end point of it. And so again, copper extends CREST by including features of the most recent federal climate plan, a healthy environment, and a healthy economy plan, or the HEHE plan. As I said and explained here, CREST was a static single period linear programming model, while copper is a dynamic multi-period framework. Really important there. As I say, it really considers the evolution, and it can tell us, what happens when we hit 2035 electric grid emissions, or 2030 negative, or 2030 zero emissions, and then 2050 we go zero economy emissions, right? So it's good to know what's going to happen with the grid at those 2 points, not just the beginning and the end. So what's also a couple other features that copper had brought forth, which was disaggregation of hydro by plant type, including run-of-river, small hydro reservoirs, and large reservoirs. The CREST framework didn't do this. It sort of aggregated all the hydro into one batch. We do need to consider the differences there, especially between some of our hydro-dominated provinces and British Columbia and Quebec, as well as Manitoba. Again, the most recent publication, actually, I should say we've had another one recently, but the first publication on the copper framework is provided to you in the citation below here by Reza Arjman and Madeline McPherson, published in Energy Policy in, I believe, August of last year. This is another source that we're going to go into. This is more alluding to the linking of a capacity expansion planning model with a production cost model. This has happened before. We've coupled the copper framework with a silver framework, which I'm going to speak about a little bit later. And of course, we basically were analyzing spatial and temporal flexibility issues that were assessed using curtailment, or at least curtailment analysis, I should say. And so looking at things like wind and storage capacities and trying to properly place those. And we're correcting those using using operational insights that we get from using the silver model. Again, we've provided that citation below, but the idea here is that we have a copper, we have an expansion and planning model here with copper. We're able to link that over to a production cost model and use the operations to make better decisions on planning there. So let's talk about the implementation of the copper framework. Okay, it's built using the Python programming language. Okay, it's written in the linear programming formulation, which is written in Pyomo. I think that should be common to many modelers in Canada. It's compatible with the GLPK, Gurobi, and CPLEX solvers. I know there's an arrangement of those that are going to be using these frameworks in Canada. Some of you are university. That's great. You can use CPLEX. Some of you are private organizations or maybe large NGOs, and so you may have some restrictions there with respect to Gurobi and CPLEX. But the idea here is that everyone has something to use, okay? It handles its input using CSV and Excel files, although maybe I should mention we have a coders database, and we're slowly but surely been connecting that coders database to our copper framework. And so we're maybe using Pandas data frames a little more than CSV and Excel spreadsheets at this point, but to say that we do have this option, especially for custom input. And I've already just mentioned this point where we're building this connection to the coders database. Again, this is more about the models today, but let's not forget that the coders is really the lifeblood as far as the input data and where we're going to use common standard scenarios from, okay? We have another set of presentations and videos for that. So I'm going to keep talking about copper and silver for today. So important features for the copper framework, really what separates copper from the other expansion and capacity planning frameworks here. Well, we include a national emission limit, okay? So putting a cap on the carbon there. We allow for SMR and CCS development, talking about small modular reactors and carbon capture and storage development. Again, those are some early technologies, but we do include them in the mix. We have generation technology phase out year, both nationally, but also provincially as well. We have limited thermal generation technologies, or at least, capping some of those different thermal technologies. We have minimum and maximum limits on wind and solar capacity. Again, these are sort of aligned with the renewable portfolio standards. And again, those can be assessed on the national level and the provincial level as well. Also, maximum capacity limits for nuclear generation. There's a province British Columbia has a moratorium on nuclear development. So we give you an option to pinpoint limitations for nuclear in certain provinces, since this is popular as an analysis. And also transmission expansion limits. We're able to pinpoint the different connections between provinces, but we're also able to singularly limit the expansion of all those transmission lines as well, both from like a scalar format, but also pinpointing and restricting some lines more so than others. So that's pretty nice. As far as model inputs goes, it takes a lot of model inputs, or at least a lot of data frames to take into as input. There's about 40 input files or data frames that would go into the copper framework. These inputs include things like existing thermal capacity, existing variable renewable energy capacity, and also hydro generation capacity, also existing transmission network capacity, projected demand and load growth. And then we have an ability to assess that for provinces differently as well. So you don't have to make all the provinces go up by the same expected growth. You can do that though. Potential hydroelectric greenfields, which is really supported by data that we have in coders of expected projects to consider. High spatial temporal resolution VRE data. This is a little bit wrong. So it says 2,200 cells. This is a previous implementation of the copper framework. I would say using 2018 data. What's nice is we're going through a 2021 update for both copper and for silver, but that's going to be about 2,900 cells or almost 3,000 cells. We're getting higher resolution data for that as we go from MIRA-1 data from NOAA or from NASA to MIRA-2 data. That uses a higher resolution cellular format for the whole grid or the whole globe. Of course, we're just using Canada. Hydroelectric capacity factor data by province. That's another input that we provide there. Now, what I want to show you here is at least alluding to some of the visuals that we have here for the results. There's many ways in which we can analyze the outputs from copper. It's a quite dense set of output data. But what's really important here on the left is the geospatial arrangement of your new VRE capacity that you're going to be developing throughout Canada. I think we can expect there's going to be a lot of that throughout the next 30 years or so. So it's giving yourself an idea that we have good figures for geospatial analysis and for figuring out exactly where those units are going to be placed. A little more boring figure to the right, but just to say that we're also looking at province by province data on the emissions level, hoping that's going to approach zero here soon. We also have some other results as well, some bar charts here on the right. And one thing that's more important is that we have dynamic visualizations. We're able to get through a lot of scenarios very quickly. What's really important is comparing multiple scenarios from copper. And so we have an ability to use drop-down boxes and like different load growth and transmission development scenarios so that we can very quickly see the differences in some of these bar charts or some of these capacity builds in the future. And again, just alluding to the idea, we have some pretty good geospatial maps that we can use for our analyses. More to come on that, though. Some additional notes here.
Jake, just one question from the chat. So an attendee is asking, what do you mean by VRE cells? So I guess you can answer that.
This is very important to consider. So when I'm talking about VRE cells, we view the entire country of Canada as an array of cells. We get data from Mira-2 data from NASA, I believe. And so they record capacity factor data. Actually, what they record is the parameters that you would need to use to calculate that data, okay? And so it basically has tabular or cell-by-cell data across the whole globe. Of course, there's so many cells that are arranged across Canada, okay? And so we take those cells and we take the data that comes with it. We're talking about air density data as well as wind speed. And so we can use that along with some elevation data to produce what the capacity factor for wind would be. We also get irradiance data for solar as well, diffuse, direct, and scattered, I believe. So we're taking some of these base level parameters and we have that cell by cell across Canada. I believe it's a 1/2 degree latitude by 5/8 of a degree longitude. So you could imagine there's about 3,000 cells arranged across Canada. So it's really high resolution variable renewable energy data that we have, okay? So this is also why it's a really high consumer of RAM when you're trying to run this on your machine. But as I say, we have 3,000 cells of data. We have 8,760 hours of capacity factor data, each for solar and for wind in each of those cells. And so do the math, right? You're doing 3,000 times 8,000, so you're in the millions of data points there. I hope I'm answering your question there, but I'm alluding to what I'm going to on this slide right here, which is it's quite resource intensive because of that high resolution VRE representation. There's some ways that we might be able to get around that in the future. I don't want to spend too much time on that today, but we might be able to group some of these cells into like a lower resolution, and it doesn't take as much input data. I think we have more.
So another question that Jake, before we move on. So how is it to add new constraint to both model? Maybe you're going to touch on this later. So
yeah, I mean, I think I will allude to it, but I mean, the simple answer is it's as simple as your conception of Python, at least at this point. Although I do believe that we've worked very well with some of our spreadsheet implementation to give the user pretty good pinpoint access to limit and also foster development of certain technology types. So I think it's a split answer, yes and no.
Thanks.
Okay, so I hope everybody can still see my screen here. All right, so some of these additional notes on copper, quite resource intensive depending on the scenario, okay? Sometimes large RAM requirements because of the high spatial temporal resolution VRE data, up to 64 gigabytes of RAM in some cases. So sometimes that's more than what your typical computer is going to have. Usually you have 8, 16, or 32 gigabytes of RAM. Also, you might have access to like an HPC cluster or something specialized. That's fine. You can still test things on your local machine using the Copper framework. Luckily, we have an ability for you to turn a test flag on, so it uses much less input data, and you can at least test to see that your constraints are being implemented. So the point there is, from a development standpoint, all you developers out there, you can play around with this on your own local machine, no problem, but you can put it on an HPC cluster if you want to run full max, okay? Sometimes long solve times are common depending on if you're running a full scenario, right? Also, the number of simulation subperiods heavily influences this. So the more you use, the more, resource computation, the longer that you wait, the less that you use. It all depends on what you're trying to do and what part of the country you're trying to model, right? So consideration of hydro development is a very big bloat on the computation time. So again, hydro units are represented as integer variables, okay? They're binaries, either you build them or you don't. There's no 50% of a hydro dam, at least not from Copper's perspective. And so if you include a lot more potential hydro builds, you're just bloating your computation time. So you need to decide if hydro is important for your analysis. Moving on, I hope I can go to the Silver framework. There's no impending questions. So again, Silver model, the strategic integration of large capacity variable energy resources. And again, this is a production cost modeling framework. I see a question here about what solver does it use. I'm going to answer this for both frameworks here. It can use Gurobi, it could use GLPK, it can use CPLEX. It can use either of any of those three. And as I say, depending on if you're a large private organization or if you're a public university, there's different options there for you. We'll talk about this a little more in the end, though. So talking about silver here, it's our production cost modeling framework. It's a production cost and economic dispatch framework for the electric grid. Okay, so what we're doing is modeling the operations of a static grid. Okay, so for a static grid composition, we're simulating that for say 8,760 hours of the year, week by week or month by month. And so it's specifically for the electric grid. And so MinPower, this is the origins of the Silver framework. Silver was developed on top of the MinPower framework, developed by Dr. Adam Greenhall at the University of Washington, which is originally an open source Python package. It was offered in Python 2. I believe part of the development of Silver was turning MinPower also into a Python 3 project, and therefore making Silver a Python 3 implementation as well. It's basically a power systems toolkit for students and researchers. It gives you some basic problem types here, the economic dispatch framework, the optimal power flow framework, and also a unit commitment implementation. Just giving you a citation there on the bottom by Dr. Greenhall on the original MinPower paper published back in 2012, or over 10 years ago now. And so most of that development has filtered into the Silver framework, but I mean, I'm sure he's around to still answer those questions. So there's 4 stages of the Silver framework, okay? And actually this gives it a lot of power. I'm gonna go over all of them and then I'll go back to the first one, which is important. So first and foremost, the long-term scenario planning framework, okay? You gotta understand that if you're wanting to solve a production cost model for 8,760 hours, hour by hour, it's a lot to consider all at once. So what we have to do here with Silver is implement a long-term scenario planning framework where we break that 8,760 hours up into month by month or week by week chunks. And then let me explain the rest of this and you'll see why. It basically pieces together these other 3 problem types. You start out with a price setting optimal power flow, okay, where you essentially have your price setting technologies totally sent out of the system. And so you're solving for the price setting technologies. And at this point, you're basically using forecasted VRE generation data. Then that goes over into a unit commitment problem. And so this would consider all hours of the unit commitment all at once. So if it's week by week, it'd be 168 hours. And so for the unit commitment, you have the price taking technologies in the system, in the solve. And at this point, I believe you're solving for the demand response. And then moving past the unit commitment, well, once you've solved for the demand response, now you're into the real-time optimal power flow. And so this takes the unit commitment results and also uses the real VRE generation portfolio or capacity factor data and gives you a real readout of the system. And again, we can go into that a little bit more in the Q&A session, but to give you an idea that you have price setting OPF, a unit commitment stage, and then a real-time optimal power flow stage. I mean, they're all woven together by this long-term scenario planning framework, which breaks a year up into either a week-by-week chunk or a month-by-month chunk and simulate these hours separately. Important to remember that the results from the end of one solve get weaved into the input of a new solve period based on the long-term scenario planning framework. So just to explain why that's important. Important features of the Silver framework and really what separates it from the rest. Demand response, implementation, and representation. Energy storage dynamics, which are quite important. Again, whether we're modeling with a linear or lithium ion batteries, also pumped hydro storage. And there is also some representation for, I believe, compressed air, as well as some other batteries, but it's mostly lithium ion battery and pumped hydro storage that we model. There's also high resolution spatial temporal VRE data. It's the same data that's used in copper, by the way. So that's nothing fantastic between the 2 frameworks. It's the same data. And also hydro generation dynamics, okay? Again, breaking it up between the different hydro types and run-of-river, small hydro operations, large hydro operations, also cascaded hydro operations. Really important in British Columbia. And so we have that implementation. And so this is what really separates Silver from a lot of production cost modeling frameworks. And that has a really good representation of hydro generation and also this good VRE implementation as well. Let me see what we got here. I've got a question here from Madan Gosh. Does it model different vintages? Once a plant is built, is it locked in? I'm going to get to this point. And so again, when we're simulating with silver, we're assuming a static grid representation. Okay, the amount of capacity in the wires is not changing during that simulation. The amount of capacity between the different plants is not changing. So we're not considering new plants into the system. We're not taking plants off. So when we're simulating for that one particular year, we have a static grid representation there. I hope that answers your question. Moving on, the model inputs here. And so we have a lot of model inputs to give to the silver framework. Some of them are common to what copper also receives. We could talk about that here in a sec. But what's most important in silver is really the operational characteristics, your generator attributes, right? Your ramping limits, up and down, your minimum up times, your minimum down times, what your carbon emission factors are for these different units. What's also important is your VRE input. As I said, high resolution. We also need to know, where are the plants? How much capacity? And then we have to connect the capacity factor data for VRE to the model inputs so that we have an accurate representation there. We also have inputs for non-VRE. A lot of this is basically your thermal capacity, or at least currently your coal, your natural gas, your biomass, your nuclear, also your natural gas with CCS is also represented here. You'd also see in the non-VRE your hydro. I know that's a bit of a weird one to talk about, but that would also be a part of your input data for non-VRE. Your storage capacity and also characteristic for storage, including lithium-ion battery and pumped hydro storage. Transmission detail, okay, your maximum capacity, also the reactance of your lines, the voltage of your line, the length of your line, and also how it connects to the different buses. Again, this is how it looks at the graph of your network. Last but not least here, your demand centers and load data, giving it for the different demand centers. And then how it also weaves into the different buses. Again, there's this separation between regions that have different demand profiles and then how they weave into the buses, which are then connected by the transmission wires. So having a breakdown for that into your input is important. So what I'm doing here in this next slide, I don't want to go through all of these, but to give you an idea that the silver framework has been applied in many different publications. Again, going all the way back to 2017 with an application in Ontario, Canada, looking at different VRE, but it's also been deployed internationally, being used in Lusaka, Zambia, to show that silver can be used with any amount of input data. It's just that with the EMH, a lot of our input data is geared towards Canada. However, the modeling framework can be reapplied in an international context, no problem. Also looking at silver for deploying storage assets, looking at connecting it to a capacity expansion planning model. I mentioned this earlier, in Miri et al. And also more recently with the assessment of Canada's electricity system potential for VRE integration with the most recent round of policies. Again, please feel free to go through some of those papers. We're talking about silver implementation now. It's very common to what we're seeing here in copper as well. It's built using the Python programming language. It has a linear programming formulation written in the Pyomo package, again, which is a Python implementation. It's compatible with GLPK, Garovi, and CFlex solvers, giving you some options depending on what your organization is. And again, if you're asking any questions there, we can probably give you some advice on how to approach that problem if you're unsure. We handle input using CSV and Excel spreadsheet files, but again, natively, it's mostly Pandas data frames. And so this last point of building a connection to the coders database, which we've been working heavily on, and finishing that up. So we're somewhat moving away from CSV and Excel spreadsheet files, at least for pulling it into the silver framework, although we might save it as output for categorizing the scenario. So moving forward.
So Jake, there's a questions around pumped hydropower. Yeah, so you want to read it?
Yeah, so we do include pumped hydropower. I think I was maybe just talking about this. So let me see. Especially talking about pumped hydropower. Can you upgrade an existing dam with pumped hydropower for new energy storage capacity? I believe so. There's this ability in copper to do recontracting for hydro. And so at least we can do recontracting for hydro. And I believe that there are some potential new build sites for pumped hydro storage, but we do include that in copper. And then also in silver, we model pumped hydro storage as well. It's modeled as a storage unit though, not as a generator unit. I'm wondering if that answers the question. Yeah. Okay, thank you. Moving forward. Okay, so I've got a slide here on improvements to usability. So this is just really kind of allude to, there's been a lot of development on silver for, at least the last couple of years, and really for like, the last 10 really. But more recently, we've helped to improve a lot of file path operations, and we've made silver to be really an OS independent framework. And so it has a really simplified environment setup. It comes with a really nice config YAML file. And so it's almost an automatic setup of your environment if you're using Anaconda. And you don't necessarily have to use Anaconda either. I'm pointing to some of you big organizations there. You may be forced not to use Anaconda. If you have over 200 members, they're going to force you to use V. And so you have to go back to using the virtual environment feature of the native Python package, right? And so if this is the case too, we have you set up to do either or. You can either use VENV or use Anaconda Python. Looks like we've got some different options there depending on your organization. So we've streamlined the user input. We've worked a lot on our model inputs Excel spreadsheets. It used to be quite convoluted, but we've gotten the main characteristics in our data frames now. We've set it up in such a way that we can basically copy the exact query that we're getting in our custom input to what we're getting from the copper or from the coders tools as well. I'm seeing a question here. How do you model interconnections between provinces? Is it optimized with copper? We're going to save this for a little while. We're going to save that. I've got a whole section on this. So we've also improved the object-oriented nature of generator classes as well. And added some auto-generated visualization. Now, this point is deceptively simple here, but for the longest time, you'd have to run a silver simulation. You'd have to look in the back end and look at all the Excel spreadsheet files for the results. Luckily, we've worked a lot with our visualizations to just automatically put like a dispatch stack up for you and an emissions plot, at least early on, before 2030 or so. And so we have these automatic plots that would come up for you for your real-time OPF, for your unit commitment stage, also for your price setting OPF. So you're able to very quickly view these very fast, right? And so I think it's much more usable, especially if you're working in a development environment. Additionally here, again, we've tested the model with various solvers here. And so like I say, GLPK, Garovi, and CPlex, there's options for you here. What I'm showing you here are some silver visualizations. And so this is not our full package, but very typically you're going to get a dispatch stack. And so we can show this for OPS, both your real-time and price setting, but also your unit commitment stage. And so you've got the full feature of generator types and the legend there. On the right, we have a pretty good job of also visualizing the transmission flow throughout a provincial network or a national network. It doesn't really matter there, but we have both good dispatch stacks, but also geospatial plots as well. And we also have features to be able to very quickly analyze scenarios maybe in the same year, but for different seasons, or to very quickly use tabs and drop-down boxes for you to look at different scenarios or maybe growth and load demand expectations. So giving you some real versatility there, but moving forward. So last but not least, I just want to talk about, this is both for the silver and copper framework, but this release of open source repositories that we did in early December 2022, less than a year ago. Both silver and copper have been released under an MIT open source license, fully permissive at this point. So all your commercial and non-commercial needs. It's publicly available on GitLab. Well, maybe I should show you the public repos there. There's 2 links below there for the public repos, but of course you can also link to them from our EMH website as well. So that we have 3 links there for you. Also good to mention that there's some nice user manuals there for you. Great README sections, also line by line for how to configure your environment, whether you're doing that with VENV, if you're a large organization of 200 or more, or if you have the luck of using Anaconda for your own environment management. I'd like to say this too with these two repos here. It really enables community engagement and support. You're able to fork these networks, right? You're able to, or these repos, you're able to fork it, use it for your own needs. Maybe you can consult back with us if we want to bring it back into the master branch in the future, if you've got something really nice and beneficial to the community. But that's what it is, it's the community here. And so we're really hoping that open source is going to achieve some of these problems and fill some of the gaps that we just can't fill ourselves, right? We think the community is going to help make the best decisions on what they need in their own management packages there.
So Jake, there's two questions, one on hydro reservoir model, and then another one around solving electricity market. So you want to comment on those, or you can answer later?
Okay, yeah. So how is hydro reservoir modeled as an observation throughout a whole year? Okay, so how is hydro reservoir modeled? So essentially, we would say that we have both run-of-river, small hydro systems and large hydro systems, right? Let's just say this, the run-of-river system is modeled on an hour-by-hour basis. It's pretty much must-take energy. And so you can pretty much model that hour-by-hour throughout the entire year. You have some larger units like small hydro units. And so those are assessed on the day-by-day. And so the constraint on those day-by-day hydro generators is that available generation must be used within the day or over a 24-hour period. But then you have hydro monthly or large hydro operations. Don't get too hung up on the names of these, but it's essentially a very large hydro operation or hydro dam. And so those are, of course, modeled on much longer timescales. And so typically the constraints on that are set that you would use its available generation within the month. And so what I'm saying there is that, you know, for your run-of-river systems and for your day-by-day systems, you can really run those on day-by-day simulation or week-by-week simulations. But for hydro monthly dams and larger hydro operations, those are essentially constrained on the month, and therefore you must model them month by month. Okay. Now, of course, there's questions on even larger hydro operations as well that are maybe more inter-seasonal. Now, there's some different situations in which you can change the modeling up there by using predefined set points for what your storage level would be across the year. That might be a different session for us, given we got some time constraints here. But just to say that we assess the different hydro generators differently, and they're constrained differently based on how large their associated capacity is. Let's see, there is Silver considering solving electricity market for unit commitment. Yeah, we do a unit commitment stage in the middle, so that would be correct. It does price setting OPF first, then it goes to a unit commitment stage, and then a real-time OPF. Mostly it's separated between using forecasted VRE versus real-time VRE between the price setting and the real-time. And then let's see what other questions that we have here. Let's see, how granular is the grid modeling? Wait for that, I've got slides for that. And then from Dylan Barty, I see, instead of gridded reanalysis data sets, ERA5 and Mira2, can location-specific Canadian weather files be used, such as seaweeds and CWEEDS and CWEC, for example? So the answer to that is yes. It takes a little bit of redevelopment, though, right? So yeah, it's not impossible to do what you're talking about here. I would say that as of right now, we're talking, no. But we could make some changes there and make that compatible. And I would encourage you to. I think many of the advantages that we can make with copper moving forward is a better representation of the VRE. It's good to have high resolution VRE. In some instances, in some places throughout the map, you can't develop VRE there anyway. So trimming some of that input data out and making the problem a little smaller might be nice. So let's talk about that moving forward. You want to keep going? Let's see. We got a lot of questions here, but I've still got.
Yeah, go ahead. We can park them for now. Let's go.
Yeah. So I think I've gone through this really good. So now I'm going to do is talk about some of the resolution between copper and silver. And I think this is going to answer many of your questions here. So let's just talk about this. Copper, it's an evolutionary framework, okay? And so it's an evolving grid network, okay? So very simply, you could be solving with a base year of 2020. You want to see what the years 2030, 2040, and 2050 look like. You can do 5 year integrants or steps, or 1 by 1 year steps. It's just typical because it's capacity expansion planning. You're going to take larger steps here. And so what we're going to have is for results is 3 different outputs for what the grid would look like there in that case, okay? It's telling you what the generation portfolio is, what's the transmission capacity going to look like, how much storage capacity, how is it connected, right? It's giving you a snapshot of what that grid looks like at 3 different periods along the way, okay? And so copper is really giving you a coarse representation, okay? I'm showing you this for copper national. Okay, typically we implement this on a national level. And so what we do is we have links between major balancing areas. Mostly it's province by province, but Ontario and Quebec have their own split systems there because they're large provinces. The modeler could model multiple transmission lines between these nodes, but typically we're just doing it for simplifications and abstraction. We're doing it with a single connection there. And so on the national level, we're putting in the federal and provincial policies as well. Now, there's been some ideas about a regional implementation of copper. Totally doable. People are working on that. I won't tell exactly who's doing that, but it's the same situation. You have an evolving grid network. You're giving an idea of what the snapshot of the grid looks like in 2030, 2040, 2050. We have a coarse representation, but with fewer provinces. Just as an example, maybe you want to do Alberta and British Columbia since they're the Western grid, right? So, you could do a copper implementation of this. We don't have that on hand. You have to do that work, but it's possible, okay? Moving forward on that, again, it still has federal policies here that are implemented. Also, although there's some provinces that are abstracted away, and there are still provincial policies here. Now, what's the advantage of the regional implementation? Well, you can model with more run days because you're using less input data because you're using less provinces. So you could get more run days in there to improve planning for storage, right? Or you could model more run days in seasons that are important for the chosen set of provinces, right? Maybe in areas where glacial melt is really important. You can also model with more sub-periods as well. If you have a smaller system, you get the idea. It's less input data, therefore you can do more scenario definitions or increase the resolution in another way, right? Moving forward. Now I'm talking about silver resolution, okay? So silver resolution, we're talking about a static grid network. It takes as input a static network. And so if we simulate over an entire year, it doesn't change with regards to capacity, okay? It's not going up or down, neither for transmission, nor for generation, nor for storage capacity. That system is fixed for that year, okay? For Silver National, what we're trying to do here is we take the initial results from copper and then we want to simulate it through Silver National. And so Silver National is a coarse representation, very similar to copper with links between major balancing areas, model as a single transmission line, although you could model with multiple transmission lines. Mainly what we're doing here is we're trying to solve for the interprovincial transmission flow throughout the entire nation, okay? Then we can do that and we can use that as input for silver provincial runs, okay? The idea is we're starting big with copper and we're filtering our way down to a really fine resolution simulation run with silver provincial. And then we're going down to silver resolution provincial here. It's still a static grid network, okay? It's got a finer representation than what we're seeing in silver national, okay? This isn't just, one transmission line between the provinces. This is representing the intra-provincial transmission lines, mostly higher voltage lines that are between buses in major areas. But again, it's a higher resolution than what we're seeing in Silver National. And it uses the interprovincial transmission flow from Silver National as input, as an import-export series, okay? And that's basically a fixed flow of energy and therefore a fixed dimension in the model. I can answer that more in the Q&A, but this is the idea that you're running with copper, okay? You take the outputs for that, you run it through Silver National, get an idea of what the operations will look like across the country. You extract the line flow results out of that, and then you run it through Silver Provincial, okay? And this can essentially give you an idea on the feasibility of your grid network, but also give you an idea on the production cost hour by hour throughout the year. Now, you can even do silver resolution down to the city. We're doing a project with the city of Toronto where this is going down. It's an even finer representation, but essentially this is the higher voltage level lines between buses in major areas within a city, okay? And again, lines that cross the city boundary can be modeled as an import-export series, right? Depending on how you want to approach that. But essentially it uses the intra-provincial transmission flow from Silver Provincial as an import-export series. There's this idea that you're drawing a boundary around your grid network. Any line that crosses across that circular boundary can be an import-export. And then lines that are sort of within that circle are going to be modeled by silver. And so therefore, those are free dimension and variable, right? They're dynamic variables, whereas the import-export theories are fixed dimensions, okay? So I give you an idea about that we have copper, we have silver. They can be implemented on different resolutions depending on what your modeling needs are. But kind of the big shebang here is the idea that we have these two frameworks and a real good use case is linking them together, okay? And so basically copper solves for the network configuration for multiple periods. It's a dynamic model, as you can kind of see here in this figure. It gives you a long-term view of what the grid will look like over time. And then silver simulates an economic dispatch and optimal power flow for a static network configuration over 8,760 hours. So we can take a time or a point in time across copper's timeline, maybe silver in 2030, 2040, and 2050. We can take the grid representation for that particular year, link the results over to silver, and run it so that we can see what the operational characteristics will look like. So we can determine what the production cost would be for all the generation technology types for that grid implementation for that year. Tell us if it's feasible, or if we have an hour or two in the year where we're really peaking out, we're just not going to be able to meet it. And so just really considering supply and demand side dynamics, but also considering transmission makeup as well. And so the idea here is that silver provides a check on the operational feasibility of the network, okay? We want to make sure that the grid configuration chosen by copper will run for all of the hours of the year. And copper is running on a very select few run days, so it's not able to capture all that information. Now I'm going to go and run through this. I have a set of slides here. What I'm just trying to do is give you an idea of a master configuration, how we view using these tools. You can use any of these tools in isolation if you would like. That's totally fine. But what we're trying to do is use these in maybe a more of a workflow perspective, maybe using it into a platform. And so we're really focusing on some of the interlinkages between these. So I just want to give you an idea of what that looks like here. So very typically, what we're going to do is start out with a pull from the coder's database. So we can pull a standard scenario. What we'll want to do is run that through Copper National, okay? And so Copper National will then solve for what the grid should look like, evolutionary, basically 30 years in the future, but on 5 by 5 or 10 by 10 year increments. You can then take static representations of what that grid looks like and then simulate it through Silver National and then through Silver Provincial. The idea is so that we can solve for interprovincial flow with Silver National, and then model and simulate very fine on the province by province level, up to 10 different provinces. You don't have to do that. And in the end, we're going to go through some visuals and analyze some of those results, okay? What's the typical information flow here, okay? Typically, we have this capacity expansion model, Copper Regional. It's going to mostly give us the discounted development cost, okay? Also discounted operational cost for a select few run days that are expanded to the year. But the idea is you're going to get discounted development costs for meeting some of these policies, and they'll be in like $20 or whatever the base year's dollars are. What's going to happen is it's going to produce a generation portfolio, a transmission network, a storage capacity, and different characteristics for those. Now that information there is going to be passed over to Silver and maybe a Silver regional implementation. Okay, and so this is the production cost model. It's going to take the capacity expansion model results. It's going to run it, okay, and we're going to see on a national level what the operational characteristics look like. But most importantly, we're solving for interprovincial line flow, okay? Then we're taking the results from this and we're going to simulate separately 2 different provinces, again, a production cost modeling fine simulation, and we're going to have multiple simulations here. We're going to produce the hourly production cost for each province, simulated separately, at least in this fashion. Both are going to use interprovincial line flow from Silver Regional. And what it's going to give us is an idea on the feasibility of the network, okay? Are we going to be able to make it throughout the entire year with the supply and the generation portfolio that we're given, or do we have issues there? Are we undersizing our storage with respect to the VRE, alluding to wind versus battery energy storage? Are we getting that correct? Are we curtailing too much? There's many different operational or analysis of the operational characteristics that we can go through here. And then we could potentially loop back for the copper framework. But the idea is that we have some flow of information here from capacity expansion model to a coarse representation of production costs, and then a very fine simulation of production cost model with a particular province or city, depending on your modeling needs. Now I wanted to take a minute here and talk about linking tool here, okay, or data transformer. Now the idea here is as you're going from a capacity expansion model and going to a production cost model, there's a data transformation that has to take place here because there are a natural format of output data for copper, and there's a natural format for input data for silver. They're not exactly the same, they're close, and so we have to use a data transformer here. So there exists a linking tool, and you must do this if you change the arrangement anyway. But essentially, we have a linking tool in between these two pieces that geospatially disaggregates the generation portfolio chosen by copper across a province or region to be simulated by silver. It connects new capacity to existing nodes represented in our database or for removing capacity. It selects the appropriate VRE data and also creates the available generation capacity input for hydro generators. The point is that there's a linking or a data transformer between these two models, okay? Now, I just want to go very quickly over this, is that we could do a situation where we do a coarse representation of silver following copper, and then we split that into province by province simulations. You might want to do that if you have a machine with low resources, you don't have much RAM, you don't have access to an HPC cluster. And so what you can do to connect those two province by province simulations is connect them with the coarse line flow results. Okay, so simulating the two provinces separately, but line flow data can be used as input between them to then link those two simulations. Now, similarly, you could take that whole process and you could bring it down into one process here with just one pass through of a production cost model, fine, for a regional implementation. Now, what I'm saying there is if we're doing Alberta and BC, instead of doing Alberta and then BC, you could take all the generation assets and transmission lines, connect it all into one system, and you could allow them to compete in one market, okay? Now, I want to push past that a little bit. It's just the idea that you can make it as large or small of a model simulation as you need. It just depends on what your computer can take. Now, for the last few minutes, I want to talk about where to find resources. Go to our website at cme-emh.ca. We have two public repos here with user manuals and great README sections. We have a Slack channel that you can join where you can get some pretty good notes, potential to get some quick responses there. And we also have some YouTube video links with some installation instructions, and there are more to come on the way. Again, we have that for silver and for copper. Now, how do you ask questions? As I said, join the Slack channel. Follow us on LinkedIn. We've got a good page there. Use our public repos to post your questions, comments, and concerns on the issue board. We take those very seriously. We take email seriously, but we encourage you to do these other points before you do that. That becomes quite cumbersome. What will we consider for development? Any major impending policy proposals for Canadian power systems? Development in areas that are within the mandate of EMH-CME, and fixing any major bugs that are critical to the main simulation package of copper and silver. So the major points there. Now, we won't be able to engage in all suggested areas. It's just really impossible. The energy landscape is quite broad, and so the requests that we get are all over the globe in some respects. So we'll do what we can. We're really hoping that the open source approach or the community approach will offer chances to others to develop some of the features that we cannot get to ourselves. We're hoping that these models that are in other areas, we're hoping that, if it doesn't align with a priority, that either you can link up with another group and you can take your own capacity and develop yourself. It doesn't mean that we will give you 0%. We may advise in some ways, but we're hoping that this open source community approach can alleviate some of these concerns. Now with that, we've got 5 more minutes here. I'm hoping that maybe we can take some more questions.
Yes, thanks, Jake. So maybe you want to look at the one that's already in the chat, and then if you don't have time, we'll follow up in the email summary. But I think you've answered some of those already, but if you look at those.
Yeah, absolutely. So how do you model interconnections between provinces? And so for the copper implementation, again, it views it in a very coarse fashion. It's a balancing area by balancing area with one transmission line in between them. It has a very small economic dispatch portion to that MILP, or that linear programming formulation, but it doesn't include all the hours for a year. So you're getting not too much resolution there. So just think very coarse. And it's not, it's essentially just a simplified economic dispatch. Now let's talk about the same thing with Silver National. They've used it very similarly. It's basically the major balancing areas with a single transmission line in between. Although Silver National is doing the price setting OPF, a unit commitment, and a real-time OPF. But again, it's really abstracting some of the capacity away because there's multiple lines in between those provinces, right? But we're really only modeling it with one. So I hope that answers your question there. Let's go to the next question by Christina Pearson. How granular is the grid modeling? Can you do just Alberta or just Saskatchewan? So copper, yeah, you could reformat to do just a single province. You can do that. You can do it with like multiple provinces as well. That's totally possible. For silver, typically the most important way to do it is to simulate it at the provincial level, okay? Most of these systems are really province by province, okay? So I would say if you want to just run silver on Alberta or just on Saskatchewan or just on Ontario, yes, you can do this, okay? Typically, when we run it at the national level, we're just trying to solve for interprovincial line flow, okay? So just something that's really critical as input for the provincial silver implementations. Is coders publicly available? I've been battling for data on a hydro run-of-river versus reservoir. Yes, yes, Davey Elder, that coders data is publicly available through an EULA, an end user license agreement, and then you can get access to an API, which you can then query the API for, or query the database for. Moving on large reservoir hydro model. If you have a summer peaking demand, is it taking into account for the large hydro reservoir management in winter months? Okay, yes and no. I would say no in the fact that the actual linear programming between the summer and the winter, they don't see each other. As I say, the long-term planning framework dissects and splits up the year into some digestible chunks, usually month by month or week by week. So in general, this interseasonal variability between, or this interseasonal approach to the management of hydro dams is not very well taken into account. You can do things like using predefined set points. You could have a very bare bones system that you do solve for an entire year. But you're limiting some of the input data there for silver. You could theoretically do that. You can try it if you have the resources and the time to wait. But what I'm saying there is that you usually use predefined set points for the large storage. Can the silver model be used to test grid reliability? And if so, how? So, I mean, mostly this is used when you're looking at the really core side of the power system. You can look at things like resiliency. You can look at things like, again, like flexibility of your infrastructure. Again, I can't give a full answer to this with 1 minute left to go, but yes, you can do this analysis. Moving on, is the real-time optimization after the UC stage means a stochastic representation of VRE? So I would say that there's a stochastic, I would say it's stochastic. It's deterministic in that it doesn't have a new seed each time, but there is a stochastic representation of forecasted VRE that is read in through the price setting OPF and the unit commitment problem. However, there is real-time VRE capacity factor data that is used in the real-time OPF, okay? And so there is a mismatch between forecasted and real-time, which propagates its way into the real-time OPF. Are you thinking to add distribution systems planning for copper? I believe maybe Rick Hendricks online might have a better answer to this question. But I think in general, we're mostly working on the transmission level side of things. Could you do that? Yes, you can. It just takes a little bit more development. All right, moving on. Do you get zonal or nodal results for silver? Yes. For copper as well. But again, copper is seeing it very coarse, and so balancing area by balancing area. Whereas silver provincial, you can see all the buses within a province, and so you do get node by node data. And then we got a couple.
All done, Jake. That's perfect.
Yeah, thank you.
Richard no, that's perfect. You did a great job answering all those questions like this. Awesome. I'm assuming there's other questions, of course, so feel free to reach out to us. We'll be sharing the slides and the link to a couple of our next event. Thank you so much for attending this webinar. I hope it was useful. Please take a few minutes to answer our short satisfaction survey that I'm going to send also via email later today. Thank you so much, Jake. Very informative. I think everybody enjoyed the pace and the content, and we'll see all of you very soon, hopefully at another event of the EMH. Thank you so much, everybody. Have a great day.
Have a good one, everybody.